Let us look at product in normal form. So given a matrix A, we want to find two matrices P and Q such that the product P times A times Q gives us the normal form. That is a matrix with an identity block in the top left corner and zeros elsewhere. Let's look at this normal form in a little bit more detail. Now, remember, reduced row echelon form gives us an equivalent matrix with identity formed by the pivot columns, not necessarily adjacent to each other, since we use only row operations. So this was an example we had seen. So row reduced echelon form of A is equal to this matrix, let's say. The pivot columns, the first column, second column, and fourth column correspond to an identity matrix, but they are not adjacent. So the matrix is not in block form. Row operations cannot change the positions of these columns. Now, 3 and minus 2 cannot be eliminated using row operations without disturbing the pivots. If we try to make these two 0, then these will not remain 1. But using column operations, we can bring the identity to the top left corner and zero the non-pivot entries on the right of the pivots. So when we carry out the necessary column operations, so basically interchanging column 3 and column 4 and doing some additional operations, making 3 and minus 2 0, we end up with this, which is in a perfect block form. We have the identity of order 3. We have 0 matrix of 3 and 1 order. Then we have 1 by 3 order 0 matrix. And we have a matrix of 1 by 1, where the entry is 0. So here, I sub 3, this 3 is the rank of the matrix A. If we had got the perfect identity without any 0 columns or 0 rows, then rank would be 3. If we had arrived at this as a normal form, then rank would be 2. And if we had this, then again rank is 3. And in this case, rank is 2. So in general, we can write the block form of the normal of a matrix as I sub r, O sub r times n minus r, O sub m minus r times r, O sub m minus r times n minus r, where r is the rank of A and r is always less than or equal to lower of m and m. So that was normal. So that is what it means. A matrix with an identity block in the top left corner and zeros elsewhere. Now remember, in RREF, there can be non-zero entries in non-pivot columns, whereas in normal form, that is not the case. Now let's look at the product in normal form, PAQ. So let's start with an example. We have a matrix which is of order 3 by 4. Now we want PAQ, which gives us the normal form. So to begin with, we take A is equal to I sub 3 by 3 times A times I sub 4 by 4. Expanding it, we get A matrix is equal to identity times A times the identity. Now we start carrying out the elementary operations. Now, whenever we apply a column operation, we apply it to the left-hand side matrix, and on the right-hand side, we apply it to the matrix on the right of A. So C2 minus 2C1, then we apply C3 minus 3C1, and then we apply C4 plus 2C1. Now, what's the objective of applying these operations? To convert this or to transform the left-hand side matrix into the normal form. Now we apply row operations. Now when we apply row operations, we apply it to the left-hand side matrix and the matrix on the left of A on the right-hand side. Again, the which operations we apply depends on how to bring these into normal form. So again, we are applying column operations. We apply these operations to this, and we apply the operation to this to arrive at these two matrices, R3 minus R2. So now if you notice that we have arrived at the normal form on the left-hand side, and we have arrived at a matrix as the prefactor of A, and we have arrived at this matrix as the post factor of A. LHS is in normal form. So that means P we have found, Q we have found, so that when we take the product PAQ, we get the normal form. But let's verify it and see whether does it actually work out like that. So we have A, we have P, we have Q. Let's multiply PA first. So multiply this and this, we get this matrix. Now we multiply the product of PA with Q. So when we multiply it, we get the normal form. That implies that PAQ is equivalent to the normal form. Now here, remember, P is obtained from row operations and Q from column operations. PAQ is useful because it reduces a matrix to its simplest structural form, revealing rank and separating independent and dependent rows columns clearly. In the above example, if we consider AX equal to 0, a system of linear equations, then the number of equations, if you look at this matrix, and if we treat it as the coefficient matrix, then rows map to equations, columns map to variables. So we have number of equations equal to 3. We have number of variables, let's say n is equal to 4. In the normal form, number of independent equations equal to the rank r equal to 2. Free variables n minus r, which is equal to 2. So free variables basically map to these two columns, all zeros, 0 columns. So out of 3 equations, 1 is redundant. This normal form is pretty useful. As we go along, we will see specific applications of this. So that was product in normal form.